Welcome to CS 1401 Video Lecture 4.1, which is about programming languages. So far in the course, we've been solving problems by writing algorithms in pseudocode. But because pseudocode is informal, we can't run this directly on a computer. Remember that a program has to be a finite sequence of step-by-step, executable, and unambiguous instructions. And pseudocode might be step-by-step, but it's certainly not executable, and it's probably not unambiguous. So we'll need to implement our algorithms in a language that the computer can process. This means looking a little at how a computer works. Here's the overall architecture of a typical computer. And there are some input devices and output devices. That's how we get information in and out. And they could be typically things like keyboards and mice on the input side, and video screens and speakers and so forth on the output side. The main part of the computer in terms of actually processing is in what's called the Central Processing Unit, or CPU. And it typically consists of a control unit, which determines what's going to be executed, and then the arithmetic logic unit, which does calculation. There's some memory typically in the control unit, which is called registers, but it's very fast memory and it's very expensive. And most of the program is kept, and the data, in fact, are kept in an external memory, which typically is kept in an external memory called RAM, for random access memory. There's also external storage. Most users of computers have lots of files that are too big to store in the computer's memory, like videos, photographs, text files, audio, pretty much everything. And because it's too big, all this stuff is too big to fit in the computer's memory, we put it in external storage and call it into memory when we need it. External storage consists of things like flash drives or hard drives or even solid-state drives. Looking at the control unit in particular, when the control unit is executing a program, it goes from step to step, executing instructions one by one. And when an instruction involves arithmetic, the control unit sends this to the arithmetic logic unit, called the ALU. Each instruction executed by the control unit is an operation, and it's represented by what's called an opcode. And that's just a number in binary, which represents what the current operation is, like doing an addition or storing something in memory. Now, I said that the opcode is typically in binary, and that's an example of what's called machine language. At the very lowest level, what the control unit works with is machine language, and this operates at the level of bits, the individual ones and zeros by which computers represent data and programs. And the whole point of the modern computer architecture, dating back from their origins, is that the data and the program are represented in the same way with these ones and zeros, and they're stored in memory. So I mentioned that the control unit had registers, and those are used, they're basically very fast locations for memory in the CPU that store values and intermediate results. Also at the machine language level, the program can say which register to store a value or an intermediate result. Machine language, in terms of operations, has very low-level machine instructions like add, subtract, divide, maybe square root. It also has labels and conditional jumps to express control flow. There might be something we're going to do which depends on the state of the computation, and we need to be able to say where in the program to go if something is true. Machine language typically lacks memory management support. That is, how to move things from memory to external storage or from the registers to memory and so forth. And the programmers have to do that themselves using machine language instructions. So what's an instruction? An instruction consists of an opcode and an address. So an opcode, for example, is get a value from some location, or add, typically things that are in registers, or put a value in a location. The other part of the instruction is the address. That is, that's the location in memory where a value will be accessed or stored. Assembly language is one level of abstraction up from machine language. Basically, it's just a kind of simple encoding of machine code into something more readable, where we have human understandable, or at least more understandable, labels for storage locations and labels for places in the code. So for instance, where a machine language instruction might have an opcode that's a binary number that, say, we could represent digitally as 35, then in assembly language there would be a symbolic label for that, like store, for example. And where a machine language instruction might have a binary number indicating the address, there in assembly language we could have a symbolic label for each address. For instance, $T0 would be a register in the CPU's memory. Even though assembly language is better for humans to write programs in than machine language, it's still not very convenient, especially if you're going to write big, complex programs. Now, it's true that people still write programs in assembly language, and programmers do that when they need something that's perhaps something that's very low level in the system and it has to run really, really fast and really, really efficiently. But for most programming, people use what is called a high-level language. And by high level, we mean higher level than assembly language. The good thing about high-level languages is that they have names for almost everything. Variables, the types of data, subroutines, that is, decompositions of things to do that I've called either methods or functions. They have constants, that is, values that we can just refer to by label, and modules, being able to break down complex tasks into subparts. High-level languages also enable us to write complex expressions with multiple variables and multiple operators and comparisons and logical operators and so forth. High-level languages provide convenient ways of expressing control. They have control structures such as conditionals, switches, and loops. And later on in the semester, we'll be looking at how to do all of those. High-level languages also provide support for more complex data structures, including composite types such as arrays. Arrays are basically ordered sets of values, and they turn out to be very efficient and very useful. Finally, high-level languages also provide abstract data types, modules, packages, and classes. These provide the tools for building more complex programs using more abstract concepts. And we'll look at those as the semester goes by. As an example of a high-level language statement, let's take a look at translating our pseudocode for calculating body mass index into a Java statement. So the first line is our pseudocode statement where it's an assignment using the left arrow character as our assignment. And the next line is a statement in Java that uses the equal sign as the assignment operator, uses the slash and the asterisk as operators, and the parentheses are used to show the priority of executing the operators. And the statement is terminated with a semicolon. Here's another example of the relationship between high-level languages, assembly languages, and machine language. If we have a statement in a high-level language, something like A sub 300 equals H plus A 300, and we'll learn about this later, but those are basically array indices. So the top statement is a high-level language statement in Java. That statement is taken by something called a compiler, which translates it into assembly language. And here's the assembly language that this Java statement would get translated into. Then the assembler takes the statements in assembly language and translates it into machine language, and the first set of values there is what it looks like in if we look at it in decimal form. And then the next set is exactly the same thing, but how it looks in binary form. So the decimal way of looking at it is a way of sort of understanding what's in the binary code. But if we translate the binary code into decimal, that's what we'd get. So to recap, compilers transform high-level languages into assembly language or machine language instructions. And there's also something called an interpreter, which does the same thing. Now, a compiler translates the entire program at once, and then that program is run later. An interpreter translates the program in the high-level language statement by statement, and it runs each translated statement incrementally. Now, I've been talking about statements, and we've seen basically one kind of statement so far, which is an assignment statement. But there are other kinds of statements as well. So in addition to assignment statements, we have conditionals, which help us decide when to do different things. Repetition, which provides ways of looping if there are things we want to do over and over again. There are statements that help us define variables that have kinds of structures, and we already talked a little bit about arrays, but we can also create other kinds of structures called objects, which have a different organization, and we can define those organizations ourselves. And there are also statements that define sub-processes, implementing the kinds of things we're doing with decomposition. And ways of doing that in programming languages are typically called methods in Java, or in other languages they're called functions. So I've mentioned that there are different kinds of languages. And in this class, we're going to look at least a couple kinds. Java is an example of an imperative language. That is, it says, do this, and then do that. Other kinds of languages are called functional, and they operate not by saying do this and then do that, but rather providing an expression in a functional notation and then having the computation proceed in order to evaluate that function. A third kind of language is a logical language, and one example, probably the primary example of a logical language, is called Prolog, which stands for Programming in Logic, or Programmed Logic, and we'll be looking a little bit at that over this semester. And basically what it does is evaluate statements in terms of being true or false, and in order to do that it will do some computation. There are also languages which are called object-oriented. And Java is a kind of object-oriented language. It lets us define more complex structures and define methods for each of those structures where they can access information in the structure and do some computation. Not all problems are solvable most easily in every programming language. If we know the problem, the kind of thing we're trying to do, we'll want to make a choice of programming language. What kinds of factors would we consider? Well, there are really four. The first is readability. How easy is it for a human to understand what the program is saying? And we already know, for instance, that machine language probably isn't that readable. Assembly language is more readable, but not as good as a high-level language. And different high-level languages have different levels of readability. You're going to see a little bit later on that Prolog in some ways is a lot more easy to read than Java. The next factor is writability. And what we mean there is how well does the language fit the domain and the problem we're trying to solve? Do the programming elements, the structures, the expressions, the statement types available in the language fit what we want to do to solve our problem? Similarly with writability, does the language provide the kind of support for the abstractions that we're going to need? A third factor is reliability. Other languages, some functional, provide easier ways to check for errors than other languages. And both of these factors, provable correctness and being able to check for errors, contribute to improved reliability of the programs we're writing. The fourth factor is cost. And by that I mean there's the cost of the programming language itself, but there's also the cost of the person power we need to be able to develop the system or program in that language, and that cost will vary as a function of the fit between the language and the problem. So that's a little bit of a look at programming languages, and in our next video we'll take a look at environments which programmers use to create programs using these languages.